In this tutorial, we're going to be working with the magnetic field due to a straight wire. Imagine we have a wire, and this wire has a certain current that goes in a certain direction. And we want to find, for instance, the magnetic field in a point P, which is in some place near this wire. And this, for instance, this will describe an angle, for instance, let's call theta 1, and an angle here which we can say is theta 2. We're going to use Biot-Savart. So remember that in Biot-Savart we can grab, for instance, a small piece of the wire, which is a differential of wire, and that the unit vector r, right, is going to be, for instance, the unit vector that goes in the direction of where is the differential towards the point of evaluation. And of course the ds goes in the direction, for instance, that goes the current. So this is Biot-Savart law, and mu0 and I over 4b is constant, so the only thing that matters right now is ds cross r over r squared. Let's see, for instance, the implications of all of these terms, right? ds in a cross product with r, for instance, we're taking this, right? This example, where remember that the cross product is the magnitude of ds times the magnitude of r, which, since it is a unit vector, is 1, times the angle, the sine of the angle, right, which is between these two vectors. So it's a sine of, for instance, I don't know, alpha, which is complementary to theta 1. Or we can state, for instance, this is ds times the cosine, right, of the angle theta 1, theta 2, or whatever. Well, theta 1 is, for instance, the upper limit in the integral, theta, or the lower limit in the integral, theta 2 is the upper limit in the integral. We're taking, for instance, a generic angle theta here. So that's, for instance, the cross product ds cross r. So in this sense, this is going to be, for instance, the integral of cosine of theta ds over r squared. Now we only need to manipulate, for instance, ds and r in order to have an integral from theta 1 to theta 2. We have a triangle, for instance, and this triangle will state that this angle is the angle theta, while this is, for instance, the radial distance r, and this is, for instance, one side, which is, for instance, the distance from the wire towards point P. This is, let's call the distance A. In that sense, we can actually state that the cosine of theta is going to be equal to A over R, or in other words, we can state, for instance, that R equals a cosine, it's going to be, for instance, A over the cosine of theta. This in order, for instance, to plug it here, right? So at the very end, the integral will be, for instance, here, right, over r squared, which, for instance, is a over cosine of theta to the square. And we can cancel, for instance, cosines. And for instance, this is x, or if we take the left triangle, is minus x. In this case, for instance, we can actually say that the tangent of theta is going to be equal to minus x over a, or in other words, right, we can say that x is going to be equal to minus a tangent of theta. In that sense, the differential of x, or the differential of s, which is the differential of the arc, is going to be equal to minus a squared secant of theta. This we're going to replace, for instance, in this point. So this is going to be minus a secant square of theta, right? From here we can do a lot of things. We can actually cancel, for instance, a with a, one cosine with another cosine, which is here. No, right? Actually, in this case, we cannot cancel that. We're going to cancel it later on. But then we will have, for instance, a cosine cube here if we get rid of this guy, right? Right? So we have a to the square here. And remember that one has already cancelled with the one upwards. And cosine to the cube times the secant to the cube is, for instance, going to cancel. Because, for instance, a secant squared can cancel with a cosine squared, right? And we're going to have a very simple integral at the very end. And of course, in the differential, I am missing the d theta. A can go out of the integral, and this will be mu 0 I over 4p from theta 1 to theta 2 of minus cosine of theta d theta. And the integral of minus cosine of theta d theta is, for instance, minus sine. So b is going to be equal to mu 0 I over 4pa times minus sine of theta from theta 1 to theta 2. If we evaluate this at the very end, we get an expression which is mu 0 I over 4pa, right? Times the sine of theta 1 minus the sine of theta 2. So this is the magnetic field due to a wire. And then of course we can have thetas like p or whatever. These are in radians. Very large thetas or very large angles or very small angles, right, for the magnetic field in this straight wire. So this is the expression that we're going to end up with.